Okay, so we have a cyclic quadrilateral A, B, CB, and the diagonals intersect at P. I don't know why I thought that was like the fourth problem. Okay. So we'll call that P. And then the circumcircle of APD. So we draw APD and BPC. And we see where they meet that. So this should be E. That should be F. I and J are the incenters of ADE and BCF. So we do it this way. Sorry, I feel like I drew this kind of sideways, but we can work with it for now. So circle of ADE, sector K, in circle BCF, P, let's call that J, and instead of H, let's call this I. Okay. And now I'll close this. IJ and AC. That was BCF and ADE. IJ and AC meet at K. Well, we want to show that that doesn't sound right. AIKE is cyclic. Did I do something wrong here? Let's see. ABCD is cyclic. Its diagonals intersect at P. The circumcircle of APB meets AB at A and E. BPC meets it at B and F. I and J are those two incenters. IJ and AC meet at K. Yeah, that doesn't look right. Let me check. So this is the 2018 problem. Okay. So it meets. Maybe there was like a typo here. Is it AIK? Is it AIJ? No. I was going to say maybe AIJB is cyclic, but maybe it's FJIE. Ah, that would make a lot more sense. Yeah, I think it's probably FJIE. Although that doesn't look like it passes through E necessarily. Oh yeah, then what would K be? It could be that someone wrote what the problem should be in the on Art of Problem Solving. Can someone check? Yeah, do you guys want me to click this? Hopefully I won't see like a solution, but I'll go check it. Let's see. Let me pull it out so that you guys don't all see if it has a solution. Whoops. I'm waiting for it to load. Wrong. It's hard to tell. Blah, blah, blah. Something I think was defined wrong. Okay, I'm just going to look at it really quickly. So someone has a figure here. So we have AIK. Oh, this makes it look like it's correct. Oh, you know what? Yeah, this makes it look like it's true. Wait, A. What if AB is longer than CD, like that?
Maybe the word segment has its importance.
Because now it kind of looks like it is true. So yeah, that's weird. So yeah, I'll just assume AB is like bigger than CD, like that. And then it kind of looks like it's true. So maybe it's like just a configuration thing. Yeah, I wish there was a way to rotate stuff in GeoGebra. Yeah, no, I really should do that. I'm gonna undo a bunch of stuff.
The problem statement is correct. It says segment AB. That's why.
Ah, so it has to intersect a segment. Okay. So this is B. This is D. And we draw some circles. Okay. And we call this E and F. I got to draw these again. And then, okay, so I need the segments to intersect. Let's see, how can I make it easier? Segments I, J, and AC. If I go like this, does that help? What if I do like a flatter? So yeah, if I do it like this, there, that's better. So that would be point K. All right. I'll maximize it. Close this. And yeah, now it kind of does look like AIKE is cyclic. So yeah. All right. So angle AIK, it looks like we could calculate that.
RDKE linear. Okay, they're not.
Sorry, what did you say?
I said RDKE linear, but they're not.
Oh no, they're not linear. Yeah, they almost look like it. Yeah, what if I draw it like this? I kind of like this the best. There you go. It almost looks like IJ's parallel though. I don't want to make, yeah, it's hard to get everything to look nice.
It's enough to prove that PK equals to PE.
K is what?
PK equals to PE.
VK is equal to
PK.
PK is equal to PB.
PE.
PK is equal to BE. Or, sorry. PK is equal to PE. My bad. I'm guessing you got that from an angle chase.
It's an angle chase.
And it almost looks, is that really true? PE equals PF? Maybe that's just, I think that's an obvious angle chase. Yeah.
That's obvious.
So really we want to show P as the circumcenter of KEF, right? Interesting. So yeah, how do we show P as the circumcenter of KEF? So obviously DI intersects this at the midpoint. It feels like the in-center, x-center lemma might be a good way to use that. Those are both in-centers, right? Because yeah, we have to use that they're in-centers somehow. So basically, we have this circle. Whoops. Sorry about that. We have this circle, which is centered at G. So basically, yeah, because G is the circumcenter of AIE, so we want to show that K lies on that circle. And we know that, we know that H is the circumcenter of FJB. But yeah, there's a couple different ways. So yeah, basically we want to show that both these points, point K lies on this circle and this point lies on that circle. Yeah. An interesting configuration. So maybe we could show that PK is equal to P. Like for example, let's label this point L. So we want to show P is the circumcenter of KEFL. We could show that we know P, we could show easily that PE is equal to PF. Can we show PK is equal to PL? I guess how would we define K and L? Like what if we hid these two circles? Is that obvious that PK is equal to PL? Is KE, so I think KEFL is cyclic. I don't think J and C lie on it. Basically, yeah, KEFL, we want to show that cyclic. Can we show that angle I, can we show that IJ intersects BD and AC at the same angles? KFJC is cyclic too. Feels like there's just so much information here that it has to solve pretty soon, right?
KFJC solves the problem if we can prove it.
Okay, so we want to show KFJC is cyclic?
Yeah.
All right. Yeah, we have to use that I and J are both in centers. Okay, you know what? I think I have an idea here. I wonder if we can I delete the circles with centers G and H? Yes, I'll go hide them. But without those circles, how do we use, I guess it would just be angle chasing when we try to use that I as in center. Yeah. So yeah, it's really weird that we have like 3 circles like this. So whoops. And it's like, so we have a circle at center G passing through AIKE, center P passing through KEFL, center H passing through FLJB. So we use the radical axis. What if we use the radical axis theorem on those 3 circles? So yeah, I guess it's a little tricky. Can we show that angle PKL is equal to angle PLK? I wonder if, what if we draw the perpendicular? Is the tangent to these 2 circles perpendicular to IJ? It looks true. No, it's not true. You can see it right there. They're not tangent circles. They just look tangent here. Wait, are they tangent? I don't think, yeah, not necessarily. Oops, sorry.
Maybe we should define K differently.
Yeah, I was thinking, what if we define K as the intersection of this circle with AC? And then we try to show that I, K, and J are collinear. Or we could show I, K, and Like what if we define, I'm sorry.
We can define it with center P and radius PE, PF.
Oh, okay. So define it with center P instead.
Now we will prove that IK, J are collinear.
Yeah, or we could show that AK and C are collinear. I think it might be easier to, I'm not sure. But yeah, I'll hide that for now. So yeah, we could also show that IK and L are collinear, and then by the same argument, we have JK and L are collinear, and then that would show I kind of like that idea. So showing IK and L are collinear. Yeah, it's not that easy. So we know angle PKE. Oops, sorry.
Can you draw the segment PC?
PC. Or what segment?
BC.
BC?
No, it's D.
DC, sorry. My bad. Maybe that's tangent to the circle. Oh, interesting. So that passes through those 2 points.
It's angle chasing. PC is angle sector of NCF.
PC is the angle bisector of DCF.
NCF.
MCF. So
Yeah.
P is the end center. If we extend DE and CF, then P is the end center.
Yeah, I said that to prove MN and or on this circle.
Oh, to prove that MN is on that circle. Okay. Yeah, it's just angle chasing. Okay. Can we show that PG is perpendicular to KE? Yeah, if we can show PG is perpendicular to KE, I think that would solve the problem.
Yeah, we know that's true because we defined K as PK K equals to PE, and from angle chasing, K is on the circle of AIE.
Wait, did you just say K is on the circle of AIE?
Yeah, it's angle chasing.
But that would solve the problem. We're trying to show AIKE is
No,
cyclic.
but we are trying to prove that IK and J are collinear. We change
Ah, okay. So we can draw those circles.
yeah, they may be useful.
Yeah. So yeah, it almost feels like angle chasing here once we know all that, because we want to show angle IKE is equal to angle EKL. Angle IKE is 180 minus angle IAE. And angle EKL is half of angle EPF, which is an EPF. I'm sure we could get by angle chasing is it's like 360 minus DPC minus DPE minus CPF. Yeah, that okay. I think we've solved it. So, all right. I'm gonna write it up. So I'll call this K prime. And okay, so first of all, we have angle PEF is equal to angle PDA. PDA, which is equal to angle PCB, which is equal to angle PFE. So that means that PE is equal to PF. Draw the circle with center P and radius PE equals PF. Let it intersect AC at K prime. And I don't even think we need L here. Let me delete this circle. Wait, wait, I wanted to show that I, K, and L were collinear. Okay, so first, yeah, I don't think we need M and N actually. So first, so let G be the midpoint. Okay. So angle EK prime L is equal to EPL over 2. which is equal to DAE over 2, which is equal to but first we have to show AI, K prime, and E are cyclic, right?
Yeah, it's from angle chasing too.
Okay, so that because angle PK prime E okay, so I'll just outline it right now. And then I'll fill in the details. So sorry. By an angle chase, A, I, K prime E is cyclic. I'm going to fill this in later. I'm just writing it out for now. And then I'm going to copy that angle chase that you just wrote. Whoops, sorry. So I, K prime, and L are collinear. And all right.
You write L prime.
L prime.
Yeah, we defined L as actually L prime.
Okay, L actually isn't even in the problem, so
Yeah, for symmetry actually, it looks more beautiful.
it looks better. Yeah, I agree. All right, so I will call it L prime. I'll say AC at K prime and BD at L prime. All right. Okay. Okay, so here's the proof. Yeah, no, I agree. Once you know the angle, the phantom point trick, whoops. Okay. EK prime L is I'll just make all the L's L primes. So EK prime L prime is EPL prime over 2. That's DAE over 2, which is 180 minus I K prime E. And so then that's cyclic. And then so I K prime and L prime are collinear. And then Similarly, J, K prime, and L prime are collinear. So then that means that K prime is equal to K, which means that AIK is cyclic. All right, you guys want to go back to the problem that we didn't solve, or do you want to try a new one? Let's see. So we have this problem. New one. Okay. I'll try this one. So I didn't do LaTeX for this yet. So let O be the circumcenter of ABC. And D is a point on the internal bisector. Where's the bisector? All right. I'm going to close that. And now I have point D, and E lies on BC. So OE is perpendicular to AD. And DE is perpendicular to BC. So, OE is parallel to AD, I'm sorry. OE is parallel to AB, and DE is perpendicular to BC. Right? So that point right there, maybe I could, there we go. Okay, so that's E, and K lies on EB, so that EK is equal to EA. See someone writing in the chat. So D is fit. OE is parallel to AD. Wait, why is D fixed? But OE, D is any point on the, I guess I don't think D has to be fixed. E is the intersection of the parallel line through O to the angle bisector. And oh, because E lies on BC. I'm sorry. Yeah, you're right. So there's only one possibility for okay, so E has to lie on BC. See how that works. So yeah, I mean, really we should. So I'll just do it like this. So I'm going to delete point D for now. I'm going to just call this E, and then then drop the perpendicular. So like that, I think, right? Yeah. All right. Okay. Let me minimize it a little. K lies on EB such that EK is equal to EA. So that's K. The circumcircle of ABK meets BC at P. I should have drawn the whole line, not just the ray. So this is Q. Let me make P look nicer. So yeah, I'm going to want to hide let me hide a couple things here. I think I want to hide that circle, right? Yeah. All right. That. OE and AD are AD is an angle bisector. I think that's good. Shrink it a little bit. Hide. We don't need the whole. AOED is an isosceles trapezoid. Interesting. And we know AO is the radius. So we want to show that PQ is tangent to the circumcircle of ABC. All right. So that's an interesting observation. So AOED is an isosceles trapezoid. And whoops. All right, so yeah, the key is using that EK is equal to EA. So that gives us some information. So angle AKP is equal to angle KAE. I wonder if KA is also tangent. No. So what can we say about EAK? EAK is EAB plus KAB. But yeah, I mean, that's a really big insight that AOED is an isosceles trapezoid. So basically, maybe we want to draw the center. Let's see. Let's draw, okay, so AKD. What if we draw the center of circle E?
Can you draw the midpoint of AD?
Yes.
Maybe it's on
Just,
BC.
so yeah, the midpoint of AD. I don't think it's on BC, although it's close. But yeah, FG is perpendicular to AE, right? Is AKB similar to ACQ? So one of the angles is equal. Let's check another angle. You have to do it that way. ACQ. Yep, they're similar. So that is the key, it looks like, to solving this. So ACQ is half of AOQ. And let's see. So, but wait, but AKB is AKE, which is AEK, which is AEB. Or we can write AKE in terms of AEB. So yeah, it is because EK is equal to EA, or AK. I'm sorry, AKE is KAE. Let's see.
Can you delete P?
Delete G.
Yeah.
Right. Yeah, I think, yeah, we want to show what you were trying to say, that AKB, angle AKB is angle ACQ. I wonder if KAC is a right angle.
Can you draw AE?
AE
Yeah.
is DK equal to DQ. Let's see. Yes. I think we're close. Is KAP 90 degrees? No. So if DK equals DQ, that's the same as saying that angle KAD is angle DAQ. Maybe we could use the isogonal line lemma, because basically we want to show AK and AQ are isogonal, right? KED and DOQ. So we want to show DOQ is a right angle. Interesting. So I think we're very close. So So can we show ED is equal to the radius of ABC?
Obvious.
Oh yeah, okay. So DE is equal to OQ. That's what we were saying about the isosceles trapezoid. So yeah, one of the sides is equal. Can we show another thing is equal? I know we're almost out of time here, but let's see. DO equals EA is equal to EK. Okay. So yeah, two of the side lengths would be the same, and so FO is perpendicular to AQ. We want to show DO is perpendicular to OQ. So angle. What if I draw, I think I really should draw this point right here. So we have angle DKP is equal to angle DA, maybe phantom point with Q. Maybe. define it to be similar and then show, or define it so that triangles are congruent, and then show that it lies on the circumcircle of ABC. Think about it for just a second. So I should probably draw. So OG is parallel to ED. In fact, I think OGED, yeah, OEDG is an isosceles trapezoid. So we want to show that OQ is perpendicular to OD. Yeah. Yeah, we want to show that's a right angle, because then angle DOQ is 360 minus AOQ minus AOD. So you think we should define it as it is in the problem, basically, right? So do we have a solution? Does that solve it? I know we're out of time, but if I'll just write out a quick summary of so we have AOED is an isosceles trapezoid. Oh, okay. All right, I'm just going to write out a couple things and then just leave it to the viewers since we're out of time. So we have that, and we have AE OD is equal to AE is equal to KE. And we also have ED is equal to OA is equal to OQ. Oops. And we want to show that triangle QOD is congruent to triangle DEK. All right, I'm going to stop here. I think we're really close, and I think Serdar's idea has a good chance of working. But yeah, we had a lot of participants today, so this is really, really cool. So thanks everyone for participating and having such great solutions. I think Serdar might have just finished writing the solution. I'm not 100% sure. Yeah, it was great having so many people this time. So sorry for the interruption in the middle. But yeah, I hope to see you all next time. So have a good one.
Yeah.